Swayam Prabha. Digital India. Educated India.
Welcome to the 18th lecture in mechanics of materials. The last lecture we started looking at how a beam will deform and what are the stresses that a beam develops. In particular, we were looking at the stresses that a beam would have. Okay. In particular, what we did was we exposed a cut surface, or we introduced a cut surface in the beam, and we exposed the traction vector that is acting on that beam. The cut surface was essentially a cut surface along the x direction with the normal as the x direction as shown here. Okay. And then we wrote what are the stress resultants, and we wrote the global moments and forces that are acting on the beam on various cut surfaces and the boundary of the body. Okay. In particular, we saw that we said that the stresses are acting only on the top surface of the beam, that is on the positive EY direction normal alone. There is some stresses acting on the beam, that too there was only a sigma YY component of the stress acting on that surface, that is applied loading. Okay. And then when you introduce a cut in the beam, somewhere here we saw that the traction that is acting on the beam, will change its magnitude as well as the direction, okay, as shown here. Okay. In general, the traction was given by an expression like this, which is the usual expression you get when you have Ex as the normal to the cut. Okay. Now, this traction is acting over an area given by Ax, wherein it is, I assumed here to be a rectangular cross section with y and z oriented like that. Okay. That is, it is acting on a cut surface here. For example, if you take this as the beam, this cross section area is where the sigma xx acts, this cross sectional area is where sigma xx acts, sigma xy acts and sigma xz acts. Okay. This is a beam, you are loading it like this, you are loading on the top face. So, basically what is happening is the beam is bending like this. Okay. So, what are the stress resultants for that? The stress resultants are the net force and net moment that will act at the cut surface because of this traction. Okay. The net force that is acting in the axial direction is given by P, which is sigma xx dAx. The shear force is Vy and Vz are the shear forces. These are the shear forces. This is the axial load. Okay. So, basically the shear forces Vy in the cut surface acts like this, and the shear force Vz in the cut surface acts like this. The axial force P acts in this direction. Okay. So, those are the stress resultants, those are the stress force resultants. Similarly, you have stress moment resultants, which is the torsional moment T, which is given by this expression in here. The torsional moment T is given by the expression here, and then you have the moment mz acting along this direction given by this expression here, the moment mc given by this expression here, which is a moment. So, basically this is y, this is x and this is z. So, mc moment will produce a deformation something like this. This is the mz moment deformation. Okay. My moment on the other hand will produce a moment like this. You can see it deforms in the plane. You can see that it deforms in the plane. Okay. Mz moment produces a moment like this, wherein the deformation would be like this. Mz is like this, My produces a moment which is like this in the plane. The moment My produces in plane deformations. Okay. And then due to the traction force acting on the boundary of the body, the y direction, wherein that area is given by Ay, it spans in the xz plane, there the net force F is given by this expression, wherein we introduce another symbol Qy, which is integration of this sigma yy over the width of the cross section, that is over this width you are integrating whatever stress that is coming in, and your net force per unit length is given by Qy. Okay. Correspondingly, that will produce a moment mz, which is Qy times x, and mx, which is sigma yy times z into ay. Okay. Now, we wrote, so the net force and the net moments that is acting on a cut surface of the beam is given here, P acting along the axial direction, Vy acting like this, Vz acting like this, F acting like this, Fy acting like this, and mz moment acting like this, mx moment acting like this, and then mx tilde moment acting along on this face, causing it to twist like this, and then mz moment which is again acting like to deform the beam like this, mz tilde moment. Okay. So, the net equilibrium equation for the force and the moment is given by here, which we manipulated to get these governing equations for the moment and the shear force and the applied loading. Okay. Now, if there is a loading on the z plane, then you will have other Fz force and you will have other moments coming in, my tilde and mx tilde will come over there on this face of the beam. Basically, on this face of the beam there were to be some loading acting on it, there will be other stresses that are coming in. Okay. So, there will be other stresses that are coming in if there is some force acting on this surface of the beam. We consider only forces to act on this surface, that too only transverse normal to the surface. We did not have any shear stress in this direction or in this direction acting on the surface, we had only normal stress acting on the surface. That is a basic requirement for a beam to behave like a beam, for a member to behave like a beam. Okay. So, basically if it were to bend like this, I have to apply some force here, you can say I am applying some force in this direction for it to bend like that. Okay. Then there will be some other forces and moments coming because of the boundary force, boundary traction that is acting on this surface. Okay. So, this is a special case that we are considering only forces to act on the top surface of the beam. Okay. If there are forces acting on the bottom surface, again you have to include that and you have to rework all the equation that we have derived till now. Okay. So, basically this is the governing equation where we stopped in last class. Let us proceed further. I am interested in estimating this stresses sigma xx in this course, in this lecture. Estimate the stress sigma xx. This is the aim of this lecture today. Okay. So, now as I told you, you add a beam like this. I am going to represent the beam using a one dimensional representation, that is I am going to represent the central axis of the beam alone, that is if this is the central axis of the beam, I am going to represent this beam using the central axis alone. The central axis, due to the application of a load, some load acting like this, some load acting like this, would deform some load acting like this would deform into some curved shape like that. Okay. Now, let us look at a cut surface, this cut surface there, that is this surface here. What we are going to assume is, we are going to assume this cut surface how it deforms, how this blue cut surface deforms. So, we are going to assume how this plane sections will deform, how this blue line is going to deform. So, basically what we are saying is plane sections normal to the neutral axis remain plane and normal to the neutral axis. Here I have used the word neutral axis. What this word neutral axis means is, neutral axis means this red line is a neutral axis here, the line about which the stress is the stress sigma xx is 0. Okay. We will see once we derive, we will see why such a axis will exist in a beam, but for now let us assume that there exists such a axis called a neutral axis where the stress goes to 0, and I am giving a cut perpendicular to that neutral axis in the initial configuration or the reference configuration. After it deforms, what happens is this blue line will become into some blue line here. Okay. So, the tangent to this line at that point, okay, the tangent to the line at that point, let us say makes an angle theta with the horizontal, measure in the clockwise direction. This is theta, measure in the clockwise direction. Okay. Let us zoom in here and draw an exaggerated figure. I have this cut this surface, I have the tangent to that surface at that point, I have the blue line which is perpendicular to that. Let us say this makes an angle theta, then the angle made by this is 90 degrees with the tangent, because I assume plane section remain plane and normal to the neutral axis. So, initially it was 90 degrees here and then it will be 90 degrees here too. So, this angle will become theta. Okay. Then this displacement along the x direction, is u of x. This u of x is given by theta into y minus y naught, where y naught is, say I add my coordinate system oriented like this, y z, this location of the neutral axis is y naught, and any other location here as a distance y from the x axis. Okay. So, u of y is theta into y minus y naught. Okay. Now, if my vertical deflection here is, if this vertical deflection down here is delta, delta is a function of x, delta is some function of x, because you see that as I bend the beam, the vertical deflection is not same at different points. The vertical deflection varies along the axis of the beam, hence this delta is a function of x. Okay. So, delta is a function of x, then what will this theta be? This theta is going to be, tan of that theta is going to be d delta by dx. From, you know that slope of a line is given by the tangent of the curve at a point is given by the derivative of the function with respect to x. Okay. You know that the tangent at a given point is given by derivative of the function with respect to the x. Okay. So, theta is this. Now, there is a catch though here on what you substitute for theta. We are assuming small deformations. So, tan theta is approximated as theta, and then here the deformation is in the clockwise, the rotation is in the clockwise direction. In other words, the theta that I will get will be negative in this case, but I want a positive displacement because it is deforming in the positive x direction. Okay. Since I want a positive direction, I have to put an absolute sign here, okay, which means the theta that I get will be negative. To make it positive, I have to write it as u of x as minus d delta by dx into y minus y naught, okay, into y minus y naught is what I will get here. Now, let us look at a different section. Let us look at a section at this side. Let us look at a section at this side. Now, the tangent to that point here is something like that. Okay. Now, the cut surface deforms parallel, remains plane and perpendicular to the normal. So, it will be like this, it will be like that. Okay. Now, what happens at this surface, the theta that you measure, this is the theta that you get from differentiating delta with respect to x, that is a positive delta, positive theta. Okay. Now, for this positive theta, what happens? The deformation is in the negative x direction, you can see that, right. The deformation is in the negative x direction here, it is in this negative x direction, this is u of x. So, when delta is positive, you are automatically getting that then displacement is in the negative x direction. So, you have the negative sign put in here. Remember, y is greater than y naught, since we are looking at a point above the neutral axis. If a point is below the neutral axis, y minus y naught will be negative and it will be positive in this case for positive d delta by dx, which is right, because at the bottom you have a displacement u x star, which is in the along the positive x direction. So, u x is given by this expression here. Okay. In general, now u, the displacement vector, is given by u x E x, that is minus d delta by dx into y minus y naught E x plus delta is a function of x into E y. To be more specific, let us write it as delta of y, being a y component of the displacement. Okay.